To determine whether an equation has a graph that is symmetrical about the y-axis, algebraically, we're going to replace each x value with negative x and then simplify the equation. To understand why this is our algebraic test, let's take a look at the graph and assume that we have an xy ordered pair solution that's a point on the graph. If our graph has y-axis symmetry, then we know we're going to have an ordered pair that is symmetrical to that original ordered pair over the y-axis, where the y-coordinates are the same, but the x-coordinates are opposite in sign. Said another way, when we plug negative x in for the x values, we get another ordered pair that is symmetrical to the original ordered pair over the y-axis. To algebraically test an equation to see whether or not it has symmetry over the x-axis, we're going to replace each y in the equation with negative y. To understand why that's our algebraic test, let's look at the graph again. Assuming we have an xy ordered pair that's an ordered pair solution to a graph that is symmetrical about the x-axis, we know that we must also have an ordered pair with coordinates x and negative y on the graph. We could also interpret this by saying, if we plug negative y in for each y in the equation, what that generates is an ordered pair solution that is symmetrical to the original one over the x-axis. Now let's look at our algebraic test for symmetry about the origin. To test an equation and see if it's symmetrical about the origin, we're not only going to replace every x with negative x, we're also going to replace every y with negative y. Let's look at a graph to interpret why this would be our algebraic test, again considering an ordered pair solution to an equation that has origin symmetry. If it's symmetrical about the origin, we know we must also have an ordered pair negative x and negative y that is an ordered pair solution. So we can say that if we plug negative x and negative y in for each of the x and the y values, what we're going to get is an ordered pair that is symmetrical to the original ordered pair over the origin. So let's look at an example here. We're asked to algebraically test for symmetry about the x-axis, the y-axis, and the origin. And we're actually going to have to do this 3 times, one for testing each type of symmetry. So our test for determining whether or not we have x-axis symmetry is to plug in negative y for every y in the equation, and then simplify the equation. So in our original equation, we're going to open up a variable for y, but not do anything to the x's. Then we'll plug negative y in for every y value in the equation, simplify, and then compare that back to the original. So on the left we have negative y. Again, nothing changed on the right-hand side. And the question we're asking is, does this equation have the same set of ordered pair solutions as the original equation? And the answer here is no. We did not change anything on the right-hand side, but the left-hand side went from being positive y to now being negative y, and so that's definitely going to have a different set of ordered pair solutions and a different graph than the original. We're algebraically testing to see if we flipped this thing over the x-axis, would we get the same graph? So now let's look at y-axis symmetry. In order to test for y-axis symmetry, we're going to need to plug in negative x for every x value in the equation. So again, we're going back to the original equation. We're not changing the y's in any way, but for every x value, we're going to open up a variable whole, and we're going to plug in negative x for all of those x values. Now we simplify, no change to the left-hand side. Order of operations tells me that we have to do the exponents first, so negative x raised to the 4th power is just going to be positive x to the 4th power, but then we multiply that by a negative, so this is going to stay negative x to the 4th. Again, we perform the exponent first. Negative x quantity squared is positive x squared because we're also squaring this negative. Positive x squared times 4 is positive 4x squared, and then we just copy paste the plus 5. After we simplify, we compare this result back to the original equation to see if it's going to have the same collection of ordered pair solutions. It's the exact same equation as the original, and so yes, they're going to have the same ordered pair solutions. So we are going to have symmetry about the y-axis. Now we do this one more time to test for symmetry about the origin. And here we're going to plug in negative x for every x, but also plug in negative y for every y value. So in the original equation, we're going to open up a hole for the y's, but also open up holes for the x's. So we have negative x raised to the 4th power plus 4x squared plus 5. In for all the y's, we plug in negative y, and in for all the x's, we're going to plug in negative x. And now we simplify. On the left-hand side, this is just negative y. We no longer need those parentheses. So we'll drop them in the simplify step. Again, we have negative x quantity to the fourth power. This is now going to be positive because we're raising the negative to the fourth power also, but then we multiply that positive quantity by this negative on the outside, which turns it back to being negative, so it's negative x to the fourth power like this. Again, we are going to perform the exponents first, so negative x quantity squared is going to be positive x squared because the negative is also being squared, so it turns it to a positive, and then when we multiply that by positive 4, we get positive 4x squared, and then plus 5 is just carried down. So after we've simplified, we're going to compare this back to the original equation to see if it has the same collection of ordered pair solutions. And this time again, our answer is going to be no. Because notice our left-hand side did not change at all from the original, but the right-hand side did. The right-hand side went from positive y to negative y, and that's a totally different equation than what we started with. So the graph is going to be different once we flip it over the origin. So in summary, we do not have symmetry about the x-axis, we do not have symmetry about the origin, but we do have symmetry about the y-axis. Now to verify this solution, we can come over to our calculator and graph the original equation, which is y equals negative x, and then raise that to the fourth power, plus 4x squared, plus 5. And then when we hit graph, we come up with a graph that we see does have symmetry about that y-axis. So our graph is confirming what we found to be true algebraically.